lectures. People are getting busier, so actually I see fewer people here. It's always interesting to end the class in an interesting way. So it's always difficult to do that. So I'm trying to put together a topic which tie together everything we learned in the class so far. And I hope to use this lecture to send a message that what you learned throughout the semester doesn't have to be practiced or understood in an isolated fashion, that you pick one technique, you use it for one problem, and then you pick another one and implement it for another problem. There is a possibility, or at least a way, to actually think about a grand integration to do everything together, using a technique that benefits from many different methods. So this is what I was trying to talk about. I don't really have a good name, in fact, for this new paradigm. Here I call it posterior regularization. It's a little bit smaller than what I'm trying to say. It's not only about regularizing a posterior distribution. But anyway, we will see as the story unfolds. You can see what I mean actually in this technique. But the second part of the message is accurate. It is an integrative paradigm for learning graphic models. So as we see so far, graphic models, in the classical fashion, translates to structure and a probabilistic loss function. Right? You define a likelihood function over data, but you use the structure, encoded in a graph to allow simplification in writing the Jordan distribution. Especially, you don't need to write a gigantic table, for all the configurations for discrete cases. You don't need to write a multivariate Gaussian, such as a big covariance matrix for a continuous domain. You can, design, potential functions or features based on subgraphs or cliques, in the domain, and then you write down distribution. And we said that learning such graphic models so far, are primarily, built on a maximum likelihood principle, because that's the, most common loss function we define on the graph. But as we actually already push through the lectures, we see that there are multiple ways to define alternative loss functions, right? For example, I think we already are quite familiar with Bayesian estimations. You can put a prior distribution over the model and the parameters, so that at the end of the day, you can choose to optimize a posterior probability of the, of the model given the data, right? So that's actually a different loss function. And very recently, we also learned some kernel methods, which is a new way of designing, loss function structures, over the graphical structure. And in the last lecture, we even learned a way to bring in a maximum margin principle, as an alternative to drive the derivation of an optimum graphical model. Okay, in terms of coefficients on certain features or potential functions. So you may ask, certainly all these different methods will have advantages and disadvantages. So a natural question to ask is that, can we be so greedy that we can find a technique that is sitting in the middle, that is integrating everything, that we can get benefit, hopefully, for every technique? Of course, we inherit, hopefully, not the disadvantage of everything, right? Hopefully, the disadvantage are mutually exclusive, but the advantage can coexist. That's the best we can hope for, right? So I'm not sure we know how to do that, but here are some actually recent attempts helping people getting there. And in particular, I want to talk about a particular technology called regularized Bayesian inference, where you can see such a potential to be realized. So just to say a few words to recap the Bayesian inference, we know that the Bayesian inference depend on a prior distribution over the model and a likelihood function of the data given the model, right? So this is by design. And this is partially by design or by your prior knowledge. But the prior knowledge needs to be encoded in the design. Therefore, it is also, in most cases, a designed prior distribution. And then your goal is to find a trade-off between the evidence and the prior knowledge. Then this Bayes will allow you to integrate that. right? So this is a very cool framework that we've been using that all the time. And you can see, for example, Bayesian version of any probabilistic models. We can, for example, talk about Bayesian logistic regression, right? We can talk about the LDA. Basically, if you recognize it is a Bayesian version of the older dictionary learning, the semantic latent semantic indexing, basically, right? And there are many other Bayesian models, and we also learn about nonparametric Bayesian models, which is a little bit fancier, to give you more flexibilities, as we will see in a second. So then, you can do, Bayesian inference, in fact, based on two paradigms, depending on what kind of priors we choose to use, right? In this case, if the model is represented as a finite set of parameters, then you can pretty much write down, an explicit prior over just the parameters, okay, which is a finite dimensional. And then, it is, of course, in closed form, and you can do Bayesian inference like this, as we usually do in the previous, in many of the cases, right? And so here are some examples you probably are quite familiar with. There are this conjugacy in picking the best prior, parametric prior for a likelihood function. Gaussian is matched with another Gaussian, and the Dirichlet is, and the multinomial likelihood is matched by a Dirichlet prior on the parameters, and so on and so forth, right? You can also have some priors which induce some favorable properties, such as the sparse shrinkage property can be also realized in Bayesian inference, right? You probably still remember logistic lasso regression, for example, actually correspond to the map estimation of a linear regression under a Laplace prior over the parameters, right? The Laplace prior gave you a spiky prior distribution over the center, over the zero. And if your model is such that it is rich and having potentially infinite number of parameters, then we also know that you can bring in priors to be nonparametric, right? We learned a few already, as you can see in a second. But symbolically, you can plug in this nonparametric prior, okay, in here, and then you do a posterior estimation of the model. Here, I replace the theta with the model because now not only the value of the theta is to be estimated, but also the very size of the model can also be a random variable. Of course, this formula is only symbolically true because in reality, you cannot write a closed form expression on something that is infinite. Right? You don't have a placeholder for that. So we actually resort to process definition, such as a Dirichlet process, Indian buffet process. We haven't learned Gaussian process, but it's another instances where you can basically easily construct some kind of conditional distribution of one more instance given all the other instances in the infinite dimensional feature space, such as a Chinese restaurant scenario or an Indian buffet scenario. Right? So these are basically a quite flexible framework already, for the Bayesian statisticians or machine learning people to, practice, a strategy to influence model estimation, right? So now we want to ask, we've already enjoyed basically a powerful way of influencing the model by designing the prior, and suppose we want to even have, richer properties over this distribution. Are there any other ways of doing that? For example, I can ask, can we further control the posterior distribution to satisfy specific properties? For example, it leads to, for example, a prediction that is respecting a margin constraint, for example, or maybe it shouldn't take certain values in the total parameterization space, that kind of direct control. Right? So this is basically what people would desire because you can always have some additional information, due to your training example or due to your problem that that is not easily encoded in this very general Bayesian formula. Right? So that's the problem we began with. So for that, people started actually thinking about a technique called posterior regularization. Basically, can I directly work with the posterior distribution? And it is actually not very easy, because this one is a distribution. It's not actually a point estimator of a coefficient. Say, in your lasso, your estimator will be something like this, and you can directly put shrinkage or put group shrinkage, anything on that. But now if I have a P, it is a little bit hard to impose any constraint or control on that. So one way, for example, maybe let's do a hard constraint. Say this is a space of all my distributions. Imagine this could be, this is a simplex, so it could be just the space of the Dirichlet prior, basically, right? And you have maybe all the values of a multinomial parameter in here. It's very hard to actually put a limit in here, say, hey, all my multinomial parameters has to be in this space rather than in this simplex. Actually, I don't know how to do that. Okay. And then you can, if you know how to do that, you may want to say, okay, this one is disqualified and that one is qualified. So these are what I mean by hard constraints over posterior distribution. Right. Okay, so if this is not feasible, then how about this? We can have a soft constraint, and that's usually a little bit easier. Basically, you are going to put layers of such space and until they occupy the entire thing. And you say that depending on where your distribution is in this space, in this nested layers of constraints, I'm going to receive some penalty. Right? So this is the spirit of soft constraints, which is allowing a trade-off of violation against fitness of the data. So if that's going to be something that we can accept, then here is a technique that people found to be quite interesting and potentially giving you that kind of capability. And it starts from this observation of a possible reformulation of the Bayesian inference. Okay. I want to remind you about, so at some point in this class, you probably heard about this variational representation of a inference problem, right? And for example, when we do belief propagation, we say, not belief propagation, we do approximate inference. Okay, it is about solving, very quickly maybe a query, which is a marginal distribution of a subset of random variables under a graphical model. That's basically the definition of approximate inference. But one way of doing approximate inference is to turn it into a variational problem. So what does that mean? It means that the solution lies in the solution to an optimization problem. Right? Basically, you are going to define maybe instead of dealing with your very difficult P distribution, you are now dealing with a Q distribution of X, which hopefully has all the queries easily encoded in there already. Okay, and then you are going to get Q to be the solution of some function over P and Q. Right? For example, the KL divergence, minimizing the differences between that. So this is a typical flavor of a variational solution, right? And we have seen probably other places of doing that. So, so here it turns out that the base rule, which is a pretty explicit equation, can be actually decomposed and written as a variational formula, which is this. Basically, here you can express the posterior as the product of prior and the likelihood. But in here, it is equivalent to say that the posterior is obtained from minimizing the KL divergence between the prior and the posterior minus a function over the likelihood. Okay, expected over the prior distribution or over the posterior, and then such that this posterior is a valid distribution. Okay, I'm not going to prove this. This is pretty trivial to prove. If you want to do it, you can do it as an exercise. But these two things are surprisingly equivalent. Okay, so in a sense, you can now cast Bayesian inference as here it is not an operational problem. This Bayesian inference is an analytic solution that you either do an integration in here or do symbolic algebra to multiply things together. But in here, you do Bayesian inference by solving an optimization problem, which minimizes a augmented KL divergence in the solution space that is defined by some other sets. Okay? And here the solution space is pretty natural. It is all possible, all valid, or all legal distribution, meaning that as long as this is normalizable and have every value equal and plus greater or equal to 0, and that's good. Okay, so we're going to actually now try to aggressively explore this variational formulation to actually see how we can control further the posterior distribution. Because here, now the solution becomes, the Bayesian inference becomes the solution to an optimization problem. You can now augment the optimization problem to give further control over this solution. Right? That's typically what we do. In here, you really cannot do any control because this is already well defined in a closed form. The left-hand side is equal to the right-hand side. What else you can do? You already plug in everything automatically. Right? But in here, you have to solve a problem to get this P of W or P of M. And in this process, you are giving a space to actually inject additional control points. And that's what we are going to do. Okay. So this equation or this reformulation was discovered in this paper. And even then, someone was in this paper. And very soon, people already actually realized that this might be a very interesting and refreshing interpretation of the Bayes rule, which opens up a lot of new possibilities. And here, let's look at one. Okay? And that's the reason we call it a regularized Bayesian inference. So here, I again copy the original variational definition, but I'm going to expand it a little bit more. Right? So here you see the KL between the prior and the posterior. And here I actually rewrote this term a little bit. This is the likelihood, and taking the expectation over the posterior over the model. And here I made them explicit. I plug in here, But I'm going to actually allow additional term to be included. In particular, in here, for example, P of a Q of M, which is the posterior of the model, is limited to be in some space of distribution. By the way, this is a space of all distributions, not a space of all values of the parameter. It is bigger. But this one is actually up to our own definition. In the simplest case, you would say that it is translating to all the Q all equal to this. If it is discrete, if it is continuous, you need to have some other control over the density, and then normalizability, right? Something like that. But we could actually be more aggressive. For example, here I'm setting up Q to be a different thing. What is that? It is assuming that maybe this Q distribution can be used to make a prediction, or maybe to compute some values, whatever value it could be. And then I'm going to set a limit on the magnitude of this function, which is Kasai. So this is just a possible constraint, right, over this particular function. It pretty much means that not all the Qs are valid. Only those Qs are valid, right? And then here, I can have the slacking function, which are basically defined on this, these bounds, upper bounds of certain control variable, and they can be put here to add additional control. Say this should be minimized, for example, right? So this is a constraint optimization problem, and solving that, of course, is another issue. It needs some potentially non-trivial theory of convex optimization or duality theory, but suppose we know how to do that, then this really gives us a much more flexible way of practicing a regularized Bayesian inference. So the take-home message here is that the base form of the Bayesian inference is in this way. Once we're going to construct a fancier set of the valid posterior distribution, then we are in the domain of a regularized Bayesian inference. And without further delay, I'm going to give you the example that we experienced last time. Right? In our previous lecture, we actually already see an instance of this, right? And which is called the maximum entropy discrimination Markov network. Basically, there we say that our posterior distribution is defined on the W, which are the value, the coefficients of some graph potentials. Okay, and they basically can form a structured SVM. And what I want this posterior distribution to be is that they should be solved by minimizing this term and plus a slack function. And then this posterior must satisfy this set constraint. Okay, and what is this set constraint? Well, we said that they should satisfy the so-called margin constraint, the expected margin constraint. Right? The resultant prediction from this posterior distribution, over structure labels Y, must satisfy the margin constraint. Right? And then we know that once we learned this posterior, they can be used like this to make the structure prediction. Right? So that's basically a form, a very very simple form of regularized Bayesian inference. And in this case, we say it is used for learning the structured SVM, or the maximum margin Markov network. So now we ask, can we, knowing that this particular formula is actually defined on arbitrary, posterior distribution over arbitrary graphic model, and this is just an instance of that. Can we go beyond maximum margin Markov network and do something fancier? Right. So the rest of today's lecture is to give you a variety of examples of showing you how this whole thing can go really wild and flexible and allow you to integrate anything you learned so far in graphic model class, into this, placeholder. So the immediate example is the following. Okay, recall that last time we say that, so what we learned so far is this Markov network. And we say that this, maximum margin discrimination network has a number of advantages. And last time we were able to visit two, right? So this one, the pack-based prediction is good for any, functional predictors. Basically, it's a distribution of predictors. As long as you have a posterior distribution over W instead of using a single W, you can prove such a pack-based bound, which is due to model averaging. So that's something we get already, which is not surprising. The second one is kind of a bonus. We realize that now we can play with the prior over the coefficients. And if you use a Gaussian prior, then you recover Ben-Tasker's maximum margin Markov network. Okay, but if you replace that with a Laplace prior, then you get this kind of a feasibility set of the posterior mean of the W, and then you get this shrinkage effect. You get this primal sparsity of the learned model. Meaning that if you design a high-dimensional structured SVM, not only the decision boundary depends on a few training sample, but also the decision surface itself has an intrinsic low dimensionality because many of the parameters has a zero value due to this L1 shrinkage. Right. The third one I mentioned, but I didn't demonstrate it, was that you don't have to stick with only Markov network, because what we are learning is a distribution of some coefficients, over a graphical model, and you can make the graphical model to include other auxiliary ingredients, such as a hidden variable. Right. So here I give you one example. And again, I'm going to use real-world examples to motivate the design of the model, and our goal is to now learn such a model using the framework I just talked about. So this is a problem called hierarchical labeling of websites. You can also imagine other problems such as a phylogenetic tree of people and so on and so forth. Right. So the gist of this is that you have a data set, okay, which is intrinsically structured, but your label only exists at the base level. For example, here is a website, and the label will be maybe this part is an ad, this part is an ad. In the ad, you have an image, you have text, you have a button to push, and so on and so forth. These are all the leaf level labels, right? And usually, if you want to do machine labeling, it is often beneficial to include latent structures. For example, you can say this is first a block on the right, a block on the left. That basically creates a partition of the problem into a smaller space, right? And also it helps you to understand that this one and that one is grouped together, and that one is grouped together instead of this and this being grouped. Therefore, that helps to boost the accuracy because for items that are bundled together, they are unlikely to be inconsistent. Therefore, the way you predict them will be making use of these dependencies, right? And all this kind of knowledge are due to or can be encoded by this hierarchy of latent labels. So this is a meta label, meta label, and so on and so forth, right? So that's basically by design. A experienced data miner or a machine learning guy could come up with such a model which allow you to do hierarchical labeling for web data content extraction. The difficulty comes with the fact that this is a fancier model, which if you train everything right, you can get a nice performance, but the training can be very hard. Why? Because usually your data are not labeled with all these meta labels, unless you hire people to do it, right? The label only came from the bottom layer, right? So in the good old days, what do we do with this kind of model? If we have a model like this, what do we do? Anybody can suggest a algorithm to learn this model? This is a hierarchical graphical model, right? How to learn that? With hidden variables. Don't tell me you don't know how to do that. We've been trying the whole semester to figure out the algorithms of learning various models, right? So this is, you know how to learn this, right? So this is another latent variable model, and these are observed, and these are hidden. How to learn that? A EM algorithm, right? So why not also using EM here, right? This is a tree model, maybe if not a tree, it's a graph model with latent variables. And what you do is to impute and estimate, impute and re-estimate, and we know some theory as well. It is actually doing the maximum likelihood learning, right? Okay, so now I ask, we've know how to do maximum likelihood estimation of any graphic models, which is good, but we just learned SVM and the structured SVM for maximum margin Markov network, and that seems to be better if we care about predictive accuracy. Can we learn a structured or maximum margin predictor for this model, which contain latent variables? So can we do that? So if you look at the literature of machine learning, even 10 years ago, maybe very long ago, after SVM, was popular, in the field, people already talk about latent variable SVMs, because, for any classification structure, you always run into a fancy problem where you have latent structures. We'll see later a few more instances. But imagine you have a multi-decision boundary problem where you need to use a multiple, SVM, binary SVM to make the prediction. Which one to use? The typical way is to introduce a hidden variable and indicates which one you go. And that hidden variable is not known, right? So that line of research wasn't very successful because pushing a latent variable into a SVM type of optimization problem is very, very hard. It's not only computationally very complicated, but also it's a heuristic can get you to a very, very, very big error. I will give you one example. So, for example, imagine clustering. For example, clustering, is about finding, components for different data clouds, right? And one can say, okay, I don't now have training label, but I want to learn the so-called maximum margin cluster, which makes sense, right? I want the cluster to be such that the margin between different clusters are biggest as possible. right? So that's a nice formulation. People try it. But with the hidden variable, and also due to the fact that the data is not labeled, it's unsupervised, it is hard to write down a loss function, over or define a margin over the unsupervised data, so the unlabeled data. And in particular, a heuristic based on EM type of procedure where you guess a label and then maximize is particularly dangerous. Okay, so maybe I should entertain you by asking, why do you think a EM type of idea for a maximum margin clustering is dangerous? Can you give me maybe a slightly non-trivial guess? This guess actually was what I get when I was about your stage, a grad student, because someone was hoping me to do even a thesis research on that, and I thought about it a little bit, and I conclude that it is a very dangerous direction, and that could ruin me. So I didn't do that. So now I'm asking, say, hey, go ahead and do a thesis on unsupervised clustering using EM. What would you react to?
Local maximum. It might get stuck in local.
Yeah, it's just like EM. You can get into local maximum, but it's okay, right? In EM cases, you somehow get out, or you can do something, right? Yeah, so it is related to local maximum, but I want something even more kind of alarming than that. Yes?
Unbalanced clusters. Unbalanced clusters with outliers and large margins.
Okay, but isn't that also true for even a likelihood-based cluster? If I do mixture model estimation, I can still suffer from unbalanced clusters, right? I think all you said are kind of true already, but I don't know what happened. I got into this weird insight, which I still believe in, but maybe there are people solving that already. I was thinking about the following scenario. So suppose that by random initialization, I pick 2 points. Okay, I just randomly pick 2 points, and I thought that they are labeled in different clusters. Just because I'm doing random initialization, therefore I need to impute their label. And it's very common that I got 2 clusters, 2 points, which are actually in the same cluster to be labeled the same way, a label in a different class with different label when I begin with. Then the EM algorithm in the maximum margin case is doing something very weird, right? It is going to try to find an assignment which want to push these 2 things as far as possible because I want a maximum margin. Right. So in the sense that when you commit a mild mistake at the beginning, your next step maximization is going to escalate that mistake to make them even more serious. In probabilistic inference, EM algorithm is playing the opposite role. You pick a wrong label, but you are going to maximize the likelihood of the entire data based on some centroids. Therefore, you are going to somehow reduce the likelihood of that error by making them, the assignment to the nearest center, not to push you away from the other pair, which are wrongly labeled. So that kind of intuition just tells me that it is impossible, basically, to solve the local minima problem because I'm almost always getting into local minima. I can have no way to escape. In EM, you have a chance to escape. In here, once you're stuck forever, right? So that's the kind of problem with, a non-probabilistic, maximum margin solution. And I think the insight there is that you have this hard assignment that if the points are in different cluster, they have to be in different cluster. They have to be pushed against the margin. So in a sense, if you want to solve even a maximum margin support vector machine or clustering, you probably want to borrow a probabilistic notion to allow the latent variable to be expressed in a probabilistic fashion. Right? So that's basically what this model is allowing. Now you can write down this model as a normal probabilistic model. Okay, you can introduce hidden variables, write down a joint likelihood function, and then we already know how to learn a posterior distribution based on the posterior regularization principle we just talked about, which is about minimizing the KL of your distribution of interest against the prior of that distribution, and then subject to some margin constraint or some other constraints. And the idea I just talked about can naturally be captured in here, right? So here, instead of just learning P of W, as we did in the maximum margin Markov network, you learn a joint of W and Z, Z being all the hidden variables in the middle, right? It doesn't change anything, just a bigger model with more random variables, okay? And so the loss function is, as usual, you just replace the PW with a PW and Z. And here, your expected margin constraint is now defined against this distribution instead of the marginal distribution of PW only. And it is actually not creating any serious additional trouble, because when you do the expected margin constraint, originally we are integrating over all the possible value of W. It is a model averaging over W. Now you don't care about the Z, and Z should be also integrated out. Therefore, your expected margin constraint is an integration over both W and Z. That's it. Okay? So symbolically, it does not change things much. And then when you do the prediction on the bottom level, you actually now can, systematically sum out the Z's, which you don't care. If you do care about the Z to be predicted, you just leave one of the Z out, okay, in your prediction and sum over the others. So it's a very elegant framework, fully respecting the graphic model inference procedure, but in the loss function, you have this part, which allow you to inject a margin constraint, right? And this was actually a very nice instance of the posterior regularization, which tells you how flexible it can be to deal with both the target distribution, also to inject posterior regularizations on the distribution. Again, the inference algorithm can be a little bit tricky, and I invite you to read the paper, but the main idea is still a EM one, right? So you have two components now, P, W, and Z, and you can basically make a factorization assumption, right? So that these two are multiplicative, and then that makes the whole thing very simple. Basically, what you do is an alternating procedure. You are going to keep one component, for example, PZ constant, and solve that. And once that's the case, you are effectively solving what we learned from last lecture. It is just the fully observed maximum margin Markov network, right? And once you now know the PW and you only care about P of Z, then you can just write down a formula, and you will realize that it is just a standard LP program that you can also solve very quickly. This alternating. So just to realize, this alternation is not alternating like a EM, which is on the value of the assignments, which can be dangerous. This is alternating between the two modality of the distribution, okay, which has a nice kind of cushion to adapt, to accommodate some errors and some initialization, local minima and stuff like that. Right. So that's basically a new model. So the experiment, as always, need to be provided to convince people it is useful, and that's what we did. And actually, the outcome was quite surprisingly good. So to compare, again, it's not very easy because there isn't a competitor. People know it is hard to train, therefore not too many solutions available. So here we find a few solutions. This one is the partially observed hierarchical random field, conditional random field. Okay, so this is doable because the conditional random field is a probabilistic model, and you put some more additional latent variable there, you can make them trained in the conditional likelihood way as well. Just doing more step of EM. Basically it's a partially observed conditional likelihood function. So its performance is in here. The other one is the hierarchical CRF. What is that? So this CRF is actually trained by providing all the labels, including the labels in the hidden variables. Okay, we are basically providing more information into the conditional random field. So for people who actually still remember the CRF, you probably realize that training a CRF is not as easy as training a HMM, right? Even it is fully observed, you need to do inference, because you are going to compute the expectation of potential functions, right? And now making the CRF partially observed can make things even harder, but it's doable. If you do it, you get a pretty bad performance. And here you have a fully observed CRF, which is also doable, but it takes a lot of cost in labeling the hidden nodes. Okay? And it is actually not as good as ours, which is this red line in here, for a very interesting reason. Right? So supposedly this blue curve is using more data than the red one, because the red one is the partially observed Markov network. We're not using the internal labels. This one is using the internal labels, but still not as good in terms of performance. Why? Because the training criteria is based on conditional likelihood, not based on a maximum margin principle. So sometimes the model becomes less predictive, especially in the structure domain. The only one that is as good or even better is hierarchical maximum margin Markov network that is fully observed. So when you add all the latent variable, when you also train it with a maximum margin framework, you get the expected good performance in here, which is a little bit better than ours. But remember, this pink curve is using the latent label, whereas the red curve isn't even using the latent curve. Right. So you can see that this performance of the two approaches are quite close already. And if I ask you to choose, you probably ought to choose D because it requires less data. Right. And this curve is just on another different error measure. At the different, this is for every average F1 on every entry. This is a block accuracy on every block on the web page. And here I kind of divided the performance, the accuracy on the prediction on different entities in the web page, including name, image, price, and so on. And this graph is mainly to show you that the spread out or the benefit or the loss is spread out over different labels, rather than that you do very well on one and do very poorly on the other. It is really quite a uniform game across different labeling tasks. All right, so that's kind of an instance I want you to hopefully appreciate. So the key message here is that, by manipulating now this target distribution, and also by manipulating this constraint feasibility set, you can now apply the principle of maximum entropy and maximum margin learning to any posterior distribution and any prior distributions. Okay, so with that, I'm going to now give you the bigger picture and then try to go a little bit more wild and see some fancier instances. Right. So here, let's see how can we now find a approach to start integrating all these different tricks that we learned so far. Right. So already, I think we are in here and here. Right? And we know that once you are in the business of a maximum margin estimation, you can try to solve the dual problem and expose the dot product between features, and where you can replace stuff with kernels. Right? So kernel actually can also play. All right. So now what I'm going to show you is to give you a few examples of plug in different components here, and here to allow different well-known fancy models people like to be boosted, with additional power. Okay, using the same amount of data just by changing the training paradigm, so that hopefully you will try to you can find a motivation to start boosting or upgrading your own model. So the first one is this very fancy, very popular nowadays, latent subspace model. Okay, so what are latent subspace models? Okay, if I give you names, you probably come to realize. So, for example, topic model is a subspace model because it is projecting the data into a topical space, which is latent. And deep neural network is a subspace model, right? Because you are trying to, again, bring the feature into some, feature space, and then try to do inference over there. So this is actually meant to refer to a large class of fancy models people are playing. Now I'm going to do two things for that model. First, I'm going to make this model to be trained in a predictive fashion. Because when you train latent space model, in some cases, you only want to visualize the latent space. But in most cases, you are trying to use the latent space representation to make predictions. For example, in topic model, your goal may be try to find a topic vector for every document so that it can become short and semantically interesting. But still, I want to make a prediction on the label of the document. Right? And there are other applications as well. And then if that is the case, I'm going to now introduce a margin criteria to train the model such that they are pushing the limit to maximum margin. Okay. All right, so here are instances of the models I talked about, I'm about to talk about. And you can see it is really not limiting to any specific instance. And here is a text topic model. These are fancier version of topic model applied to image. And these are, at that time it's called the harmonic model. Later it's called RBM model. But it is an undirected version of the latent space model. And now let's assume that our goal is to make a prediction, such as what is the content in the image, what is the label of the document. And in that case, you want to hopefully train the data in a supervised fashion, train the model in a supervised fashion. And these kind of training labels are quite prevalent nowadays, right? For example, for the text documents, there are often discrete or continuous scores or ratings of documents. And for images, of course, there are labels for image contents and stuff like that. So the goal is how to integrate this label into a model and then push the margin as best as you can. So just to review, this is the original LDA model we all are familiar with. And here is a supervised version of that. In fact, the supervised topic model was proposed already by David Bly and John McAuliffe, in the following graphical model. Okay, basically now instead of only modeling the document itself, which are the text, the words, you also get a label somewhere. This label, in their case, is a discrete. I think in their case it's a score, okay, of rating, for example. And then you can basically assume the rating comes from the bag of word topics. Okay, the Z are topic indicators, and the combination of that, leads to a prediction. Okay. And then what they can do is to write down a likelihood function of this, okay, and then try to learn the topic model in a unique fashion. But just by looking at this, you can just simply say, okay, I like the likelihood formulation, but I further want to push the prediction to be maximum margin, right? So to do that, you basically now inherit this L term, which is the original, Bayesian inference. Remember, the Bayesian inference is about, writing, getting the posterior, minimizing the KL divergence between the posterior and the prior, and plus some other terms. So now which is summarized in here, okay? But in addition to that, I'm going to now bring in the following stuff. Replacing the trivial constraint on the posterior of the topic, which is on other hidden variables. Here the hidden variables include the topic, theta, the indicator Z, and I think that's all. Instead of just define a posterior space that all this distribution can be valid, I'm going to introduce these constraints. I say that the prediction out of Z using this eta coefficient vector leads to a Y label, and that prediction score must be bounded by a margin, okay? And likewise on the opposite margin, opposite label, and so on and so forth. And this margin has to be bigger than 0. And here I have a slack function to be minimized. Okay. So that's basically turning the LDA, the latent distribution allocation topic model, into now a maximum entropy discriminating LDA. Okay, it's a supervised topic model with maximum margin included. And you can see the components, the design is fairly straightforward. You have the model fitting components, you have the predictive accuracy components. You can do the same for not only regression model where the prediction is a score or a rating. You can also do a classification where this Y is just binary labels or multi-way labels. So in that case, what do? Well, this predictive function becomes a logistic regression function, right, rather than a linear regression for the continuous thing. And that doesn't change things too much. without giving you the details of the derivation, you can see the effect. So here are, these are topics. Okay, topics are basically this beta, which is supposedly representing different topics, in a corpus. And then one of the utility of the topic model is to give you a visual display of all the documents, all the data that you collect in a point cloud type of fashion, so that you can visualize the pattern. So here, this is the embedding of a few thousand articles, okay, in the top 2 topics learned by LDA. And this is a projection of the same data in the top 2 topics learned by MED-LDA. Okay. And what are these data? This data come from the 20 news group. There are 20 clusters, okay, in this data. And each color represents a cluster. So what do you conclude from here and here? If I ask you to build a classifier, okay, of the documents for this 20 news group, which projection do you prefer to use? Just by intuition, by just eyeballing the data. The one on the left, surely, because that's my stuff, right? No, that's not a good reason. So the real reason is that here you can see the point cloud. The data are not separated very well, right? If you look at this particular case, you can see all these different colors get cluttered. And it is impossible for you to find a good classifier, even in a nonlinear way, to separate, for example, the green stuff from the blue stuff and other colors. In here, at least you can see the colors start to form, self kind of aggregation, and it is making your life a little bit easier to at least find some boundaries, between different colors like that. And in here, well, you draw green here. What about this? What about that? That's fine. So there are all these different, and this is 2 dimension. If you talk about more dimensions, you actually are going to expect this one will separate even better. Right. So the moral here is that by this margin constraint, due to classification, I now had a bias in the projection of the data into topical space. I also have a bias in learning the basis of the topic so that they make the data more discriminative. Okay. All right. And these are just visualization. The actual proof actually comes from the numbers. So you can actually now perform classification and regression, and you can actually compare the differences, okay, using different algorithms. And I have a lot of curves. I'm going to show you only one so that you can hopefully extrapolate to the other ones. So this is a pretty difficult comparison experiment. The baseline is always, you do LDA. That's what people typically do. You do LDA first. You get the topic documents projected into a latent space, and then you run a second stage SVM on that. Right? That's usually the natural thing to do. You get your data projected from a word vector into a topic vector. You run SVM on the topic vector, and you are done. So we put this as a baseline. Okay. And the next one is the disk LDA, which is the disk LDA and the supervised LDA, which are the 2 probabilistic motivated supervised topic model, okay, which are actually modeling, the predictive label in their training of the topics, which actually creates already nice bias. But it is based on a maximum likelihood principle rather than a margin principle. So they outperform the baseline, but not by too much. And this is the result from the MED-LDA. So I have 2 curves for MED-LDA. So the MED-LDA basically, at the end of the day, gives you a theta for every document, right? And also it gives you the Y prediction directly from the model. So on the red curve, this one, I'm basically directly using this Y, okay, from the MED-LDA model to answer the label query, okay, and the performance is in here, okay. And then I could also have an alternative. So I still have the theta here, right? I could ignore the Y here and pass this into another SVM and then get a Y. That's another artificial second stage kind of a processing. Surprisingly, I didn't get much over that. So why that's the case? Basically, here I'm almost like using the SVM twice, right? the SVM is already in the training of the theta. Now I'm using that again to, make a label out of the resultant theta. And this curve kind of suggests you that your original meta LDA is already exhausting the benefit or the information in the training data in the max margin fashion. Therefore, using another SVM isn't giving you additional mileage. Okay? And this result is kind of comforting because that means the maximum margin information is actually playing a good role already in this stage. You can see the same thing actually for regression as well. This is a four-vector regression instead of just a linear regression. And the people worry about timing. Okay, so it is actually as fast as the topic model in terms of training time, because it is iteratively doing the latent variable imputation and the topic estimation roughly in the same way as what topic model would do anyway, okay, without doing additional probabilistic inference. Here, the supervised LDA is much more expensive because it is an overall joint probabilistic model. You need to now do a serious probabilistic inference over the latent variables, in which case we don't have to do. Okay, so I have some other graphs for fancier topic models. Here you see all the plates and nodes, errors for an image oriented topic model. Again, without showing you the detail, you can see that the same thing can happen. You can introduce margin constraint and the label, and you get a performance that is in here, comparing to all the alternatives that is in here. Right. And likewise, you can train a RBM. Okay, now with the same principle, RBM is about having a predictive kind of label in here, but then have the hidden layer as if you have the one layer neural network and then all the features at the bottom, right? And usually, neural network is not trained in a supervised way, or RBM. Therefore, you have only these two layers. But if now you are making the neural network for making prediction, you can directly put the label on top of it, and then you can suddenly train a discriminative RBM, the restricted Boltzmann machine, right? And with that, these are the topics you can learn actually out of the pictures, which are pretty clean and consistent. Number-wise, you can see that the maximum margin Markov RBM is actually, again, dominating most of, if not actually all the alternative approaches. Okay, so retrieval, that's a different task. You also see a curve that is dominating alternative approaches. So up to here, I think I ran quite a few examples to show you that this maximum margin, maximum entropy training through the regularized Bayesian inference or the posterior regularization can actually be generalized to all, interesting parametric graphical models that we run into. Right? We've run into topic model, restricted Boltzmann machine, and image topic model, and the hierarchical, labeling tree model and stuff like that. And they are universally all generating good results. Questions? Before I show you a few more examples, what next example you expect to see? So we've gone through all the parametric models already, right? So the next thing should be, what about the non-parametric models, right? So I'm going to show you something even more fancy now. So there is actually, again, a high-level kind of division of machine learning territories, right? People say, okay, I'm an SVM guy, and others say I'm a graphical model guy, and usually these two domains don't talk to each other, but from last lecture and from I talked about so far, looks like SVM and the graphic model coexist. They can somehow work together. But then you probably also heard people say, I'm a non-parametric Bayesian guy, I'm a division process guy, or I'm a person doing Indian buffet process. And that seems to be another territory which is self-sustaining, so they don't have to work with others. So now I'm going to show you that even those fancy things like DP and the Indian buffet process can also be integrated into this framework. And the notion is very simple, right? We have this variational formulation of the base rule, and one component in that variational formulation is the prior. And so far we've been staying with a parametric prior. What about replacing the prior with non-parametric one? you can plug in Dirichlet process and infer process, right, to be the prior. And it turns out that works equally well. So here I'm going to give you 2 examples for doing that, which results in 2 interesting models. One is called the infinite SVM. The other is called the infinite latent SVM. And by the way, they are for classification and also for feature selection jointly with classification. So I'm going to probably say a few more words on this one, and the next one I will just quickly pass that. So we run SVM all the time, right? We know it's very good, but sometimes you probably wish you have additional leverage on SVM. So here is an example for that. So one of the good kind of character of SVM is that it deals with nonlinear functions, right? You can plug in a kernel function, then it can generate quite sophisticated decision boundaries, so that data as complex as this. Here I have 3 classes, and you can create a highly curvy boundary to separate these 3 boundaries, these 3 classes. That's nice. Okay, that's actually done as a free plug-in kind of a practice. You just choose the right kernel. But people also realize that when you do this, it is sometimes giving you a risk of being overfitting, because simply these functions are just too rich, too powerful. Okay, if you have some outliers in here, they can actually also remember that. So you may be deceived by a good training performance, and then my testing data may just drag the performance down, okay, due to overfitting. Then people say maybe I shouldn't use this very fancy a single SVM with kernel boundary. I may want to use a combination of simpler SVMs. So here are a mixture of 2 SVMs, okay, a mixture of 2 linear SVMs. Basically, I'm going to set a boundary in here and set a boundary in here, and at the end of the day, I'm going to first examine which one I should use, and once I'm in the right domain, I'm going to use just one of them. Okay, so this is achieved by introducing an auxiliary hidden random variable, a pivoting point to choose 2 options. So this model is a lot more simpler than the other one at the cost of a hidden variable. Okay, and you may actually be still unhappy with this one because this is too simple, and you may fail to capture some of the subtle fluctuation here. Then you can plug in a low order nonlinear kernel, right? So here you can see this mixture of 2 RBF SVM, but this kernel is a lot simpler than this one. Therefore, chances for this to be overfitting will be also smaller than this one. Right? So this is basically argument for a practice on mixture SVMs, and that's particularly useful when you have multiple modalities of the data or multiple classes. Then you really want to set multiple decision boundaries, each being a single SVM, possibly using kernel to generate some nonlinear effects. Okay, so once you have a mixture, the question comes, right? How many components I have to have? So that's kind of always a very intellectual question. That's interesting. And so what people do is to, in the mixture model, for example, for density estimation, we know we can set up a Dirichlet process prior, so that the number of components can be automatically inferred, right? But here, I'm not really running a density estimator. I'm training different support vector machines, and my loss function is actually the margin of the data, how I can basically play a Dirichlet process in that. Right? So that basically creates you, a very interesting problem, which now can be hopefully symbolically solved in a very straightforward fashion, right? So going up again, back again to this variational formulation of the base rule, right? So we know that we need to have this, we need to choose this one, and we need to choose a constraint set. And basically, the decision you need to make is to choose the model, choose the prior, choose the likelihood, and choose the posterior constraint. That's basically all you choose for a generic posterior regularization, exercise. So in the case I talked about before, sounds like you have a natural choice, right? So your likelihood function in here is going to be now a latent classification model built on a mixture of SVMs. Okay, you treat the SVM as a density function for you to define likelihood of the data. Basically, the likelihood is defined on whether I am on the right-hand side or the left-hand side of the boundary. That kind of function can be written. I will give you examples in a second. But then you don't know how many components you need. Therefore, you choose the pi of m to be now a Dirichlet process. Okay, let's just symbolically imagine we can deal with this process. There are, of course, when you do inference, you have a special way of plugging them in, but such thing at least exists. But and also the likelihood, of course, is a Gaussian likelihood. You're capturing noise of the data on each side of boundary. That's pretty standard. But the most important thing is that I don't want to lose the unique nature of the SVM kind of property, right? The maximum margin property. So now the resultant distribution must give a prediction that is satisfying margin constraints. Okay, so that's the whole point. And then once you have that, things become pretty clear. You are going to now write down the model, and this is a graphic model representation of the latent space model. You have data points, label, and you have this z, which is the latent indicator on which boundary you are going to use. And depending on that, you are going to write an appropriate generating function from the feature to the data, and from the labeling prior to the actual label, and so on. So these are, I suppose you know how to do that already, in our earlier class of graphic model. Just follow the graphical design and then write down the drawing function. And then what's important is this is a component classifier. If you know a component, you are going to use that to make a linear prediction based on the SVM idea. Here I wrote things in linear. When you solve it, you can actually see the dual function to expose the kernel property, then you can plug in a kernel. Right? So I'm not going to write it here. And in the infinite dimensional case, you are going to now sum over all possible selectors. Right? It's going to sum over all possible component classifier. And again, here I can symbolically express that. And this is the discriminant function resultant from this predict function, and they has to satisfy the margin constraint, which is in here. Right? And that's basically what we have. Again, the algebra can be a little bit tricky when you actually you want to go from here to the actual solution. I can give you just maybe one word. The trick is to use some kind of approximation to the Dirichlet process, which is a stick breaking process, if you remember. Right? The stick breaking process tells you that you can chop the stick into smaller and smaller pieces up to a point where there are only very small amount of residue accounting for the rest of the components. You don't care. You truncate from there. And then that can basically enter your posterior distribution of this infinite SVM. And then you basically plug in everything into the previous equation, and the results is here, right? So you can see that comparing to other standard SVMs and so on, you get a good accuracy improvement. Even without really any sophisticated additional modeling ingredients. Just basically turning the training into a maximum margin training. All right. So that's basically an instance of integrating now the nonparametric Bayesian prior with posterior regularization. And I have, as you can imagine, more examples of practicing this. For example, here I have a new example of learning latent features, which I don't want to really spend my time on. There are too many examples now. Basically, the idea is that plug in this with an indent buffet process. Now, your goal is to not only, so I have a feature entry, okay, I'm going to not only select a component classifier for that, okay, and also I'm going to do feature selection on this particular feature, on this particular data. Remember that in the indent buffet process, it allows you to select feature for every different data points. Remember this big table where I have an infinite number of features. And then the first data point will select some feature. The second data point will select some other feature, and so on and so forth. Right? So you can now have an approach to jointly do this feature selection plus a margin-based classification resultant from this feature selection. And this whole thing can be done by just introducing a ending buffet process as the prior, which is roughly playing the role of controlling the features. And the model itself is a latent feature model where you have the this Z matrix as a feature selection function to plug in the appropriate feature to the appropriate data points. Right? And of course, this model follows a ending buffet process prior. Okay, so with that, here are just some equations showing you how to plug in the right constraints to form the expected margin constraint, and also to solve the posterior regularization problem in this particular setting. And here the results kind of demonstrate a improvement in the classification performance, but more importantly in the form of a feature selection property. You can see that the data is intrinsically of lower dimensionality. The performance actually stops once you reach to a certain amount of features. Okay, and the rest of that will be pushed to 0 in their feature weights. Again, the model itself is not that important. The main message is that now you see this posterior regularization framework is really quite open. It can be really playing with different choices of the building blocks in the prior, in the likelihood, in the constraint, and so on. So to summarize, I think that's a good time to end this semester's class. We now at least see graphic model to be practiced in a Bayesian way, in a kernel fashion, in the maximum margin fashion, and also there are good formalism to allow all this to be played either pairwise together or all together using the regularized Bayesian inference principle. And here is a summary of the instances that I showed today to hopefully make the case of such a design. So that's basically all for graphical models. So what do we want to get out of it as a result of this whole semester of 29 courses? So I figure I want to conclude the course with this summary. So after all, at the end of the day, at least in my opinion, the purpose of learning or study machine learning is not about writing fancy papers with intimidating equations or maybe a good curve on benchmark data set. Right? It is really about solving open problems with good performance. And usually when you are in the wild space of open problems, it is actually sometimes overwhelmingly hard to find a starting point because you have so many choices. So here I listed a few choices which constitute the element of learning. Right? You have the task which actually isn't made explicit to you. Sometimes you go to a company and the boss will tell you, I have the data, go to find a way to improve my revenue. They don't even know how to do that or what kind of task you are supposed to solve. They ask you to define it. So it is your goal to really now boil down to embedding, classification, clustering, topic extraction, all this kind of thing. You have to be clear to yourself, what exactly you want to solve. Okay, and that's actually the first step. You want to start defining your problem. And then you need to now look at your data and to worry about representations of the data. Do you have supervision or not from the data? Do you have constraints from the data, priors, and so on and so forth? And depending on the type, the availability of those data, your task and your model choice can also be highly different. For example, if you have the label already, you may want to take a joint margin and likelihood approach. But if you don't have any label, then forget about it. You can only do probably likelihood-based learning. Right? And then the model paradigm, that's basically the holy grail of this class. We learned so many different models for multivariate distribution. Right? And there can be an overwhelming amount of different options for you. And many students, even experienced researchers, sometimes get disoriented in terms of the choice. So you want to, again, study your task and the problem, and hopefully make the simplest possible choice that can satisfy your goal, instead of pushing for just fancy formalisms. And then once your model is done, you need to now start talking about the objective and loss function. Usually these two things are taken together as a kind of convoluted kind of statement or design, but I prefer to decouple it. Okay, the model usually corresponds to the feature design and the dependency structure and other knowledge engineering on your domain. But the loss function can actually be more flexible than just a default likelihood function. So we learned now conditional likelihood, margin, and other kind of loss. And this can be actually applied to almost all the different models that you use, rather than staying with what their original label originated from. Right? And then once these are all in places, you are ready to think about the inference problem. And again, this is the biggest mistake I see actually among many practitioners. When we talk about a problem solution, sometimes people say, I want to solve this by a EM algorithm, or I want to solve this by convex optimization. I don't know why they say that, but maybe to show off a certain degree of knowledge. But without even choosing the model and everything, what EM was for, what optimization was for, actually isn't really clear. Or sometimes you can see even a paper published with a title, say, solving problem X with MCMC. And I have to say, if I'm the reviewer, I have to decline a paper, because MCMC is a workhorse algorithm for many, many models. How come you can solve a problem with that kind of thing without even mentioning the name of the model? Right? So again, I want you to hopefully learn the art of decomposing all these different elements, settling down each component in its position, and then start worry about the other components. For example, now you've already have an optimization function, you have the model structure, you have your data. Then in your choice of all the inference algorithms, you can choose variational, MCMC, optimization, and so on and so forth. And usually that's going to be very effective, because you are not going to easily change your course just by first setting down your algorithm and then change the model based on the algorithm you are going to play. This is actually the opposite direction. You want to set the model first and choose the right algorithm to solve it. If that algorithm isn't good enough, you approximate with some guided principles. Then at the end of the day, of course, evaluation is very important. I think a different model needs a different evaluation. For example, some of the evaluation may not be as informative as others. I think the topic model, for example, which is a very, very widely practiced approach, was once upon a time, maybe even now, debated in the NLP community for its utility. Because in most cases, the evaluation was based on a perplexity type of justification, which is the fitness to data. And it is not really goal-driven. Fitness to data doesn't mean you can do good prediction task, you can do good interpretation task, right? So if your goal is to make prediction or interpretation, you have to evaluate in that particular design and with that particular kind of criteria. And again, this kind of choice can actually sometimes help you to discover flaws in your model, and also can help you to make your publication experience easier, because the reviewers are more easily to be convinced. Right. So with all that, I hope you enjoyed the class so far, and you learned something for your future applications and study. And if you want to continue exploring this domain in your research, you can definitely contact me, and I'd be happy to stay in touch. Okay, thank you very much. And next Wednesday, we are going to have this very exciting symposium for project presentation, and I look forward to see you all there.